Okay. So this is lecture 9, and this is the end of our discussion on diffusion and also for process simulations. So after a short break due to the Thanksgiving Day, then we will move to the device simulation. So today's lecture will be particularly quite short. So let's go to the electric field case once again. So now consider two dopants, for example, boron and arsenic. So boron is negatively charged and arsenic is positively charged. And now the solution vector can be written as this form. So at a given position, we can place boron and arsenic. Of course, there is no preference between boron and arsenic. So although I start from boron, arsenic, but of course you can write it down equivalently arsenic, boron. So there is no difference in it. And one thing you have to keep in mind is in the case of a boron atom diffusion, so the term related with your electric field is written as hole density. So do you remember the flux for your arsenic one? So if you remember correctly, then it has certain dependencies on electron density and another electron density. But please note that there was positive and negative sign for positively charged particle and negatively charged particle. That's the reason why in the case of your boron case, you have to consider the hole density instead of electron density. But you know, in our case, we always assume NP, the product between electron density and hole density, is equal to square of intrinsic carrier density. So once you understand electron density, then you can calculate hole density, or you can directly calculate both of them. So since our fluxes has some dependencies on electron density and hole density, sorry, and these quantities can be written as a function of net charge density. So therefore, although these C terms are independent variables, however, their coefficient, this P has some dependencies on CAS minus CB. So even when you solve the diffusion of boron atoms, but you have to consider also the density of arsenic atoms. That is true for also your arsenic flux. So when you consider arsenic diffusion, also you have to consider the boron density. So they are coupled, no longer independent to each other. So let's consider one example. So consider the following initial profile and conditions. So now we have 300 nanometer thick structure and boron, p-type dopant boron is uniformly distributed. So it has relatively low density, like 10 to the 17 per cubic centimeter, and we are now assuming 1000 Celsius temperature. So at that temperature, so its diffusivity is given by this number. Okay. Then consider n-type dopant arsenic. In this case, we are having the Gaussian profile, and the peak appears at 20 nanometer away from this surface, so quite short, and peak density is quite high, 5 times 10 to the 21. I'm not kidding, 5 times 10 to the 21, not 20. So this is extremely high density. And standard deviation is just 9 nanometers. So you can find that this is really narrow distributed. And diffusivity of this arsenic atom is about one order of magnitude smaller than that of boron diffusion. So, okay, at that temperature, arsenic has a much lower diffusivity, but in this case, what will happen if we just make a certain diffusion? If boron and arsenic are not coupled, then we can just consider the diffusion of this already uniformly distributed device or species. Then what will happen? It is already flattened and uniform, so when you just hit the system, then there will be nothing. Already that is perfectly uniform, nothing will happen. Of course, in the case of arsenic, then you can expect that this upper position can be so that is just diffuse. However, in this case, we have some quantities like no flux is allowed toward this negative direction, so they will be stopped. And although here we have open boundary condition, so in this case they can fully diffuse. So we can see that if we consider just this form, we can have this kind of behavior. So I just took 10 minutes long diffusion without considering electric field effect. So then you can understand arsenic and boron are decoupled, and in the case of a boron case, the initial profile and the final profile are identical, so as you can easily expect. And here we have peak value that is now diffused. However, in this case we have the dead end, so now there is no way to propagate toward this over negative position, so you know that there is increase of density. But in this case here, you can freely diffuse, or arsenic atom fully diffuse, so you can see that there is still Gaussian profile. That is the decoupled case. So in order to solve this one, the one you need is just your status like homework number 5 and problem number 2. So already 2 weeks ago you were able to simulate this system because arsenic and boron are not interacting each other. Okay, so now you can consider the coupled the system. Why they are coupled? As I told you before, since we have dependencies on electron density and hole density in this case, and this electron density and hole density, they are depend on the doping density, net doping density, although for example n is not a single function of arsenic concentration. It's not. N is not a single function of boron concentration. It's not. However, electron density and hole density are function of arsenic concentration minus boron concentration. So now when we try to calculate certain quantities like arsenic, then what will happen? Then we will have partial derivative of our net charge density times, once again, net charge density with respect to arsenic. what is it? So C net charge density is defined as here C net, net. So net charge density, this secondary term like round C net over round C arsenic can be just written as positive number 1. Of course, round C net over round C boron concentration in this case, that will be just identically minus 1. So this is quite simple, but anyway, it means that even when you consider this quantity CB, typically you think that, oh, there is no effect because this is electron and this is boron is concentration for holes. However, it's not. So if you have slight increase of your boron density, then it means that your overall net charge or net doping density is slightly reduced, so your electron density will be decreased. So that is maintained by this negative sign originated from this C net over CCB. Okay, so please note this one. Anyway, now you can implement this coupled system, so it will take some difficulties, so please spend your time. So I think that this is not an easy task to students, so instead of just 2 days long homework due, so I will allow 1 week and 2 days. So we will have Thanksgiving Day break, and we will meet once again next Wednesday. So please submit your homework problem by the next Wednesday, not this Wednesday. Then what happens if we go the same amount of time elapsed with electric field effect? That is the resultant profile. So this is initial arsenic concentration, and this is the arsenic concentration without any electric field effect. And you can see that this one, the one with electric field effect, is slightly different. So how can you describe this phenomenon? So you can just say that, okay, it seems that it looks like the diffusivity of arsenic is enhanced, so more active diffusion occurs due to this electric field effect. We have already seen it before in the previous lecture 8. So that is okay. Now, even in the last week, you were able to solve this problem. But point is, now we introduce the coupled system. In the coupled system, we now solve boron 2. In this case, let's see what happens. So if we neglect any kind of diffusion of electric field effect, then it was still uniform even after the diffusion process is over. However, now this profile, including the electric field effect, shows some differences. What is it? So now our boron atoms are just drained into this surface area. So previously we have already talked about the direction of our electric field. That was the direction of our electric field. So positively charged arsenic atoms are drifted in this way. That's the reason why effectively it looks like arsenic are more actively diffused into the substrate. In the same time, here we have boron, and this boron has negative charge. So when we have electric field in heading the right direction, then our boron atoms are moving to the left direction. So of course in this case we have really negligible electric field, so nothing happened. However, you know, at the initial point, what was the junction? There was the junction. So we had strong electric field near in this part. So boron atoms, negatively charged boron atoms are drained into this surface area. So that's the reason why here we have actually depletion of our boron atoms nearby the junction.
정천은 어떻게 판단하는 거예요?
So junction is just
그러니까 위치를 어떻게 판단해요?
okay. So his question was how can we determine the junction between n-type and p-type, and it is quite simple. So when we have the same amount of n-type dopant and p-type dopant, then that is regarded as a junction. So for example, at this time, at the initial profile, the junction was here. After that, now we have junction here. So after some time, 10 minutes later, because you know in this case our arsenic concentration and our boron concentration are matched. So if we ask ourselves what is C net, then we will say that this is exactly 0. So this kind of way to determine the junction position is called as metallurgical junction. So yes, so metallurgical junction point is used to determine where we have the junction. Okay, so now we can understand this kind of a phenomenon when we have a p-n junction and try to some diffusion, then boron is just consumed by this n-type region. So simply speaking, now consider a two-dimensional case. Typically, we have a p-type substrate, and now we implant our n-type dopant, typically arsenic. So here we have N+. You know that this is exactly the same situation we are looking at. In the case of uniform p-type substrate, we introduce certain ion implantation of arsenic atoms that has Gaussian profile. So that was the case. Then we apply the heat. Then what happens? In that case, if we consider the interaction between arsenic atoms and boron atoms due to the electric field effect, after some time later, we can observe that, okay, this is the expanded n-type region. It's quite okay. We expected it. But point is, there is something unwanted one. Previously, we had a uniform distribution, but now we found that here, actually, the boron density is somewhat lower than we expected. So are you with me? This is related with this one. And in this graph, although it just looks like a moderate change, but please note that this is 10 to the 17, and this number is just 3 or 4 times 10 to the 16. So more than half of our original boron atoms are disappeared. So we have almost no boron atoms at this point. That can happen in our realistic situation. Of course, that happens not only this underneath, but everywhere here. We can have the reduction of our boron atoms.
그러면 거기서 리덕션 된 보론들이 그러면 어디로 가야 돼요?
Yes, as you can see here, that is just collected here.
여기서 위치가
Yes, so previously there was a uniform distribution of boron, and when we apply the heat, then borons are just drained into this part. However, you know that the boron inside this n-type region, due to the drastic difference between this n-type dopant and p-type dopant, that doesn't play any significant role. Nothing happens. It's not that important. But point is, this part here, we have some realistic effect. So let me just be more specific. Where do we have the real problem? Where do we have the real problem? Here we have still n-type region. Okay, it's okay, but point is, in this part here we have reduction of boron density. This is really p-type. There is almost no arsenic concentration, but boron density is reduced. Then let me just go to the practical problem related with this phenomenon. So here we have MOSFET, and usually we wanted to make a short channel MOSFET. So the distance between these two N plus regions are quite short. So usually we say source and we say drain, and we try to make the distance between this source and drain as short as possible. So now we have quite a short distance between source and drain. Also, what we wanted to do is just controlling our gate voltage. We wanted to control the number of electrons underneath this oxide layer and control the current. That is the ideal case. However, point is, now when we apply 0 volt to our device, what you wanted to do, well, is just to shut down this transistor, and there is no electron. Therefore, we expect no current flowing between source and drain. That is ideal case. But unfortunately, if we have too short distance between source and drain, then there is another route for current path. Previously, we assumed that there is only one path of electrical conduction between source and drain through this interface region. Okay, this is the desired and planned way to make the conduction. But if we have too close source and drain region, then starting from here, we can have the direct conduction through this channel region, not in this surface region, but through the bulk of our silicon p-type substrate. We can have a certain kind of current conduction. That is a really bad situation. So in order to prevent this kind of unwanted problem, usually for some technology, we intentionally introduce certain kind of enhanced p-type dopant. Okay, so are you with me? So although the p-type concentration is not that high in usual case, however, in order to prevent the leakage current through this body of p-type substrate, usually that component is called as punch through. In order to prevent this kind of punches through current, so we intentionally introduce relatively high doping density. This is of course p-type, so boron is implanted in the case of our n-type MOSFET and MOSFET. So now think about this one. Before applying certain heat, we had halo. This one is called as a halo, and here we have a halo p-type doping. and now we apply the heat to anneal our device. Then what happens? Although we have implanted sufficient amount of our p-type dopant, but after the heat process is over, then we will lose our halo doping. Then what does it mean? If we have the significant loss of halo doping, then yes, the punch through between source and drain can be enhanced, and that is directly related to the failure of your short channel device. Okay, so the main purpose of this demonstration is quite clear. If you neglect electric field effect, then each of your arsenic and boron are treated as just independent particles, so they are not interacting to each other. So then you cannot expect the realistic effect shown here. So depletion of our boron atoms near the junction. However, that is critically related with our realistic device fabrication. So in the case of a serious problem, we have to consider this kind of effect. Okay, so with me. So now we have many homeworks because due is not this Wednesday but next Wednesday. The first problem is please reproduce the last graph. The graph is shown here. Okay, starting from the given initial profile, please try to calculate arsenic profiles and boron profiles. So in this case, if you try to consider the exact Jacobian matrix, then maybe you will have some problems because no, it has certain quantities. So here we have electron density, and this one has, of course, this dependence. We considered this dependence in previous homework. However, now we have same but the opposite dependence on the boron concentration. So even when you make the Jacobian matrix for your boron diffusion or arsenic diffusion, you have to consider the dependencies not only arsenic but also on the boron atoms. So that will be quite tricky. So I'm afraid that if you try to make the exact Jacobian matrix, maybe many of you will fail. So as a safeguard, first try to implement an approximate Jacobian matrix. So it simply means that please neglect all kinds of all kinds of these dependencies in your Jacobian matrix and just to consider the explicit dependencies on your boron concentration and arsenic concentration. However, even in that case, you will get the solution with increased number of Newton iterations. So once you get that problem, then you may switch to the exact Jacobian matrix. So please note that you can a little relax your condition. And second problem is now you have the working code, then please predict the dopant profile after 30 minutes later. Okay, then yes, please show me your dopant profile, then I will compare your result and my result and determine whether your implementation is correctly done or not. Okay, so this is the end of our discussion on diffusion. Of course, my original plan was consider more effect on the diffusion. Up to now, we have considered the electric field dependence. However, we have another thing to be covered, originally planned. Another one is doping concentration dependence. I mean that we had diffusivity, and diffusivity was just considered as function of time only. However, for example, if we have arsenic diffusivity, then this is not only a function of temperature, but it is also function of arsenic concentration itself. So now everything becomes much more complicated. Yes, however, we have to consider this one for high doping case. Of course, if we have low doping concentration, then that doesn't matter, because this term usually this dependence can be written as this form. DAS can be written as DAS, and it's just a constant term, and DAS1, and it is corresponding to, for example, electron density dependence. And we can have also second order term, like quadratically dependent on our electron density. Of course, we can expand further and further, but in reality, usually we stop here. Then, if we have really low concentration, like low arsenic concentration, then since the arsenic concentration is quite low, so among these three terms, of course, this term or that term do not play significant role, and only the constant term will dominate. However, you know that we have already seen it when we consider electric field. When we have the significant impact of the electric field, it is also related with the case of our arsenic concentration is much higher than our intrinsic carrier density. When we have high dopant concentration, then electric field effect comes up, and also doping concentration plays a significant role, because now this factor can be much higher than 1, and then eventually this term will dominate 2. So are you with me? So in practice, when we have a high doping concentration, things becomes more complicated, but unfortunately I spent too much time on the electric field dependence, so this doping concentration dependence term, our discussions will not covered in this semester. So maybe I can refine the lecture contents a little bit further to enhance the speed of our lecture progress. And another one is, all of them are just considering the diffusion of our arsenic and boron in macroscopic view, but we can also consider microscopic view of dopant diffusion. In that case, we can consider also vacancy and interstitial for our dopants, and that is the correct view we have to consider. However, we have many things to be covered in the device simulation part, so unfortunately, of course, this is microscopic part cannot be covered in this semester, so sorry about that, but anyway, we have to stop here. Another topic we have not covered, although planned, is completely different thing, is ion implantation. So ion implantation is completely different story, and you know that here we have the initial dopant concentration in Gaussian form. Then how can we generate this kind of Gaussian dopant profile? That is done by ion implantation. And ion implantation is completely different uh, fabrication process. So in order to simulate this ion implantation process, we have to introduce a new rule. It is not like the diffusion. We have to consider the acceleration of atoms and motion inside our silicon atoms or silicon crystal. However, that will not also covered in this semester. So sorry about many missing points in this case. So anyway, even though we have not covered this one, I think that already you are quite heavy loaded due to every uh, homework problem. So I wanted to ask you, do you have any question on the lecture content up to now? So I think that these two homework, homework number 9, problem 1 and 2, will be the summary of our discussion on dopant diffusion. So if you have any question, then please feel free give me a question.
그리고 아까 그림에서 N 영역으로 P 이온들이 들어갈 수도 있다는 거죠. 그러니까 N 외에 N 나사님만 있는 게 아니고 보론도 일부 포함이 될 수 있다는 거죠. 실제로는.
Okay, his question was, okay, so previously this part is regarded as n-type reason, and this part is regarded as a p-type reason, and after this diffusion process is over, then we can find the enhanced number of boron atoms even inside this n-type reason. But that doesn't matter. Actually, whether one point is n-type or p-type solely dependent on the net charge density. So even though you have certain increased number of boron, but still this part can be safely regarded as just a fully n-type reason. So no problem. Okay. Any other question? So not only for this content, but if you have any question up to today's lecture, lecture 9, then please feel free to ask me question. Okay, then if you don't have any question, then I think that it is over. Today's lecture is over, and I will just give you some announcements. So as some of you already know, so this Wednesday we have no offline lecture. Instead of that, our lecture 10 as planned before, so lecture 10 will be on online lecture. Actually that is already uploaded in my YouTube channel. So I wanted to ask you to watch the video. It's very short. Although our normal class is 75 minutes long, but it will be just 16 minutes long. So this is just a snapshot of our lecture 10. So please watch it. But I think that since lecture 10 is just recorded and not offline lecture, so the interaction with you is not possible. So instead of considering a new topic, I just summarized some important papers published in IEDM. So please watch the video, and that is the only thing for lecture 10. And now let's go to the homework number 9, and we have 2 more problems. Problem number 3 is quite trivial. Just to leave your comment on the lecture video. Okay, then I will use your comment to check your attendance. So just to leave a short comment, it's okay. So if you have any question, then you can also leave your long comment. I don't care about the uh, length of your comment. So anyway, in order to check the attendance, please leave a comment. And problem number 4 is more serious. In that video, I have shown 11 IDM papers. They are widely distributed in its contents. So I try to carefully select each of them. So please select one of them and submit a report on your selected paper. Of course, I don't expect your report is perfect because IDM paper contains a lot of things, best content in that year, so maybe it would be very difficult to understand everything. But please just try to understand the main idea, the gist of that paper, and give me a report on it. So I just to check whether you have tried or not. And although I have selected some papers, but I also expect that some of you have your own favorite IDM paper. So I'm not quite sure, but if you have your favorite IDM paper, then please leave that one instead of this 11 selected IDM paper by myself. Okay, so are you with me? So you can select any paper, then please submit your review report on this one. All of them are submitted by next Wednesday. So now in this homework number 9, we have 4 problems, but 1, 2 is really serious. You have to implement the coupled diffusion simulator, and number 3 is trivial. You don't have to actually submit anything, so just leave your comment in this lecture video, not in your report, but you have to leave the on the video. So, and you have problem number 4, just to show you that you have tried to understand the paper. Okay, then do you have any question on homework number 9 or anything?
그 아까 N이랑 P를 커플링 시켜주는 이퀘이션이 그 전하중성 이퀘이션 이랑 NP 곱이 일정하다는 그 두 개의 이퀘이션이 N과 P를 연결시켜주는 건가요?
Okay, so his question is, in this case, let's come back. His question is, so here, electron density and hole density are related with these dopant densities, and in order to get some information about electron density and hole density, we must consider this one, minus electron density. So as he correctly asked, and positive hole density, and here we have arsenic concentration minus boron concentration. This quantity can be regarded as the net density of positively charged atoms, and this one is just showing you charge neutrality. And in order to solve this one, since we don't know N, since we don't know P, we need another one, but fortunately at equilibrium and only for equilibrium, then we can have this relation, so-called mass action law. Then we can use this relation to eliminate either electron density or hole density. So if you wanted to get certain expression for your electron density, then please just eliminate your hole density by using this expression. And if you want to eliminate your electron density, then please use this one. Then you can immediately find the two equations, and each of them can be easily solvable. Then you will find the dependence of your electron density on net charge density, and also your your hole's dependence on the net charge density. Okay, so is it okay for your question?
예.
Okay.
하나만 더
Oh,
좀.
sure. It is always welcome to
예,
give.
기계에서 이제 그런 아세니를 주입을 할 때 걔네들이 이온 상태로 들어가는 건가요? 아니면은 이렇게 뭐 예를 들어 아세닉 같은 경우에는 플러스 이온에다가 전자랑 합쳐져서 들어가는 건가요?
Okay, so usually we need. So first of all, I just want to state his question because there is also English speaker here. So let me just go to this one because it's good too. So although we have not covered the process called as ion implantation, I will make a short comment on it. So his question was, are they, I mean that here arsenic and boron, are they ionized or not? So usually, first of all, we have to understand this one. In order to implant our ions into our silicon substrate, this one should be accelerated. I mean that if they, let's say that this is arsenic atom and they are just hanging around and here, then what will happen? Can you expect that this arsenic atom can be located deep inside our silicon substrate? No, there will be just surface reaction only. However, what we wanted to do is just to precisely control the depths of our arsenic atoms from the surface region. So, in order to inject our atoms, they should be accelerated. So, in order to accelerate them, it is a good way to make them as ions and apply certain electric field. Then using this electric field, they are accelerated. Then they become quite fastly moving ions, and they have, simply speaking, they have a large kinetic energy. They are fast. Their momentum is high. Then when it is injected, then now this is silicon and this is a rigid body. So this is a rigid network of silicon atoms. However, since kinetic energy of this arsenic atom or boron atom are so large, then it can destroy actually predefined network of our silicon crystal. So now if you increase your energy higher and higher, the energy can be orders of just 10 kilo electron volt and beyond 100 kilo electron volt. You can control your kinetic energy in this range. I mean that orders of 10 and 100. Then if you increase the energy of your particle, then of course it can go deeper and deeper. And if you reduce the energy, then you will have just shallow distribution of your atoms. Okay, so simply speaking, my answer to your question is, okay, they are ionized to be accelerated, and by controlling this acceleration or kinetic energy applied to these particles, we can control the depth profile of our final dopant distribution. Okay, so are you okay with my answers? That was a really good question, although we have not considered the ion implantation in this semester. But that is a really good question. Any other question from students? Okay. Okay.
저 상태에서 전화분석이 안 일어나는 경우는 필드를 안에서 갖고 있는 실수가 아니죠.
I mean that, okay, so when it is accelerated, it is ionized. But you know, once it is injected, then inside this one. So usually what we think is, actually when that is injected, then it does not take the place of our silicon atoms. For example, think about this one. Silicon, silicon, and there is a silicon. This is a network of silicon. There are tons of silicon atoms in here, and arsenic atoms are just comes in brute forcefully. And yes, this well-defined silicon crystal is now destroyed by these alien atoms called impurity. So what we think is, okay, now we have this kind of arsenic atoms here. Once it is injected into this one, whether that is positively charged or not, this is not a matter of our concern. I mean that. So in order to accelerate it, they should be ionized. Then once this atom is located here, and its charge state is determined by now the dynamics inside this silicon substrate. So what we expect is, usually this arsenic atom at the beginning of this implantation, then it does not take the place to replace our silicon atom, although it is inside our silicon crystal, but it is not working as a dopant. Silicon arsenic is working as a dopant only when it kicks out one silicon atom, and when it occupy this position, then eventually it is used as dopant. Then how can we have this kind of thing? Yes, in order to that happens, here we have an arsenic atom, and here we have a silicon atom, the host one, and the original owner of this position, and this guy should be kicked out, and there should be an empty place for it, and this empty place is called as a vacancy. Then this vacancy should be occupied by the nearby arsenic atoms. Then eventually this arsenic becomes the real impurity inside our silicon. And this, what happens to this silicon atom? Yes, this silicon atom is called as interstitial silicon, and this one is no longer used as a member of a silicon crystal. This becomes another alien, and it is just propagating and try to take its own position. Then let's think about this one. It will just move, and there previously, for example, here we have vacancy. Then now it can consume it and become just another, just a normal member of a silicon crystal family. So simply speaking, let me just come back to your original solution. Your original question. Your original question was, here we have arsenic atoms, and actually we have inserted it. Then how about its charge state? And its charge state can be either charged or just neutral, and that is determined by solving appropriate equation for this one. In reality, this kind of and this one are regarded as a different one when we consider diffusion equation, and they can change their state from here to there, here to there. Because if arsenic atom takes one more electrons, then it becomes a neutral arsenic, and if we lose it, ionized, then it becomes ionized arsenic atom. So that is a different story. But once again, when we inject or implant our dopants, they should be ionized. And I wanted to say that although we say that this is boron and arsenic, but in many cases, this is single, instead of this single atom, we have a certain kind of different materials heavy containing this arsenic to make it heavy. That, why do we want to make it heavy? Let's say that if this is too light, then what will happen? Then if we have this kind of thing, then we can propagate further. Sometimes in these days, previously we wanted to have a very deep well. However, nowadays we are just wanted to make a really shallow junction. So previously we wanted to push our atoms deep inside the silicon substrate, but now we are more interested with how can we precisely control the depth from silicon substrate. In this case, instead of this single atom ion, but other ions are better to have this kind of a phenomenon. Okay, so we have more things to be discussed in this ion implantation, but unfortunately, we have many others in this in the device simulation part. So unfortunately, we have to stop here and move to the device simulation. Okay. However, that was a really good question, and thank you for your question. And any other question from the students? So once again, you are always welcome to ask me any question. Okay, then if you don't have any further question, although we have still 15 minutes left, but I wanted to wrap up today's lecture. The reason why I wanted to stop here is, in my opinion, or in my guess, performing this homework problem 1 and 2 will be quite tricky to most of you, because you can easily make many mistakes in its implementation. So please have your time sufficiently to do homework problem 1 and 2. This is the final summary of our all of diffusion discussion. So I just wanted to recommend you to spend sufficient time on these homework problems. Okay, then I want to wrap up today's lecture. Thank you